Hello once more. My name is Feruz. I work for Ericsson Software Technology, and this is Antti Kervinen. He works for Intel. And today we're going to talk about how can you or someone optimize the Kubernetes nodes specifically for the low latency and real-time workloads. I guess you already guessed why we're talking about low latency real-time applications because this is one of the use cases that we have as the Ericsson, our telco people. Okay, I can switch from here. The thing is, in the telco world or in general, I think when you're tackling with the jitter, especially when your workload is containerized and running as a Kubernetes workload, the jitter is something that you have to deal with quite a lot. And even the small numbers might have very huge impacts eventually on the customer side, let's say. So what we want is basically when we're running the workload or the applications as CNFs, that is called in the telco, we want the jitter to be predictable in the first place, and we want it to be as low as possible, right? Of course, it's not always easy to achieve, but there are some ways to achieve it, and this is how we're going to start today our slides. So how do we achieve basically low jitter when we have Kubernetes applications? Or in our case, again, it's a telco workload. There are existing solutions that used to work until these days, and they still are, how to say, like in practice you could still benefit from those, but it's not going to cover all of the cases, especially with the recent type of the hardware and then development that is happening on the Linux. So one of those things that, or the solutions or the approaches that somebody could apply to reduce the jitter is by starting using exclusive CPU cores for your workload. For example, what you can do is that basically you pin your latency sensitive application to a specific dedicated or their own CPU cores so that the other processes that are running on the same node do not interfere with your application. And you also avoid the noisy neighbor issues. The other approach is that CPU frequency. So you could play with the frequency of the node. Basically, you could, for example, lock the frequencies to the highest, to the maximum, and also disable the CPU frequency. That way you have the stable frequency running for your application. And then the other approach, or the last one in this list, is the playing with the C states or the power states, meaning you could turn on or disable the C states and then put the disable the sleep C states, because playing with the C states, especially like going in and out of the sleep, is gonna cause some jitter issues. So these are some of the well-known approaches how to reduce the jitter, and they used to work. Again, they still do work for some or most of the cases, but not all the time. For example, there is an issue with using the exclusive CPU cores. That means even if the application isn't really running at certain time, you still have your CPU cores allocated for that application, so your CPU cores are staying at idle. Or if you play with the frequency, for example, if you set the frequency to the highest, to the possible, and if you disable the frequency scaling, that means you have the elevated power. So you're still paying some money because your power consumption is pretty high, even the application isn't really running, or there's no need for that. So the next question is, okay, we had these solutions, so they're not fully enough for our case. What can we really do? What is the solution? How can we achieve the lowest jitter that is possible? The good news is that the Linux is evolving as it has been all the time. The hardware architectures are evolving. There are already tools that are available on the Linux side. There are already new changes that took place in the OCI, on the container runtimes. Those are really good, and we could achieve what we want with those. The problem is that they are not available easily out of the box in the Kubernetes, because there's no APIs that will give you the access to those control knobs from the Kubernetes APIs. So we have this. The thing is that we have solutions, we have toolings that could help us to reduce the jitter, but they are on the low level. what we want is that our application is running on the Kubernetes, so we want to benefit from those tools, and because we're running the application as the Kubernetes workload. Luckily for us, there is this node resource interface. It's part of the container runtimes, and this is the solution that kind of closes the gap between the tools that exist on the low level, and then we benefit from those tools for our applications running on the Kubernetes. So if we try to discuss a little bit about NRI for those of you who are not familiar with it, let's say you want to run your application, time sensitive or latency sensitive application. So you create your application, you install it as a Kubernetes pod. The pod spec automatically goes to kubelet, as you know. Kubelet picks it up and then formulates the OCI spec, and then it talks to the high level runtime like containerd or cryo, well in this case containerd, through the container runtime interface, right? And the interesting part starts here at the containerd level or the cryo level. So nowadays when you run your applications through those runtimes, alongside the CRI, there is also the NRI interface or this node resource interface. What happens is that when the request comes to the containerd, it sends down the OCI spec of your original pod to the NRI plugin, if there is a plugin that is interested on that type of the pod. So then NRI plugin picks it up, does some modifications onto the OCI spec, and then sends the modified OCI spec back to the containerd. So the next thing, what happens on the flow is that modified OCI spec flows down to the lower level runtime like runc or crun. In this case, it's runc, for example. And then it goes all the way to the C group on the kernel, and then your allocation of the resources, for example, takes place or something else. This is the regular flow with the runtime and then the NRI. So NRI is already by default on both in the containerd and cryo, so you don't have to do anything on the runtime level. The only thing is that the NRI plugin. So the APIs of the NRI are in place, but you need the logic, and that logic is hidden behind the plugin. So the plugin does different things, and then you can develop your own plugin to do certain resource manipulation, for example, and so on. So one of those plugins that really fits, for example, in our case, is called Balloons NRI plugin. What this plugin does is basically, let's imagine the case that you're creating a pod, and you have a single node. Let's take a simplistic case. From the Kubernetes perspective, the node looks like this. Basically, it has n number of cores and 16 gigabytes of memory, and that's it. But if we try to zoom in into this node and try to understand how it looks like, we might gets another picture. So here we see, actually, apart from having 4 cores and 16 gigabytes of memory, we actually now have access to the architecture of the interconnect, how the memory controllers are located, what is the distance between the memory and then the CPU, how the local access, remote access structured, and so on. It's nice to know it, but now we need to go a little bit further. We need to utilize those because, for example, placing the application in one NUMA node or in one NUMA zone might be better compared to going through the interconnect because it's much faster. So with the help of balloons, we could actually get this, first build this knowledge and then expose this knowledge into the Kubernetes and try to use it whenever we are placing our workload. So what Balloons policy or NRI plugin does is that it basically tries to create resource pools, so-called balloons, and then you allocate whenever you're creating your workload, you can attach your workload to that specific balloon. So it's basically a set of resources. So with the balloon, you build resource-aware configurations, and then the balloons can be inflated or deflated dynamically, or it could be static as well. So you could say, I create a balloon, it will have this much CPU and this much memory, and that's it, but it could be dynamic depending on the workload requirements. With this balloons policy or the plugin, again, like you have very deep understanding about the hardware topology. Like you have understanding about the PCI, memory topology, and other devices that exist on the node. And then the configuration is easy, like standard Kubernetes way. Basically, you have the CRDs, so you could configure the balloons policy itself with the format in the format of the custom resources. And whenever you're applying the configurations, those configurations could be the cluster wide, or they could be per node, or it could be node level, node group configurations. So you could apply those configurations more than one node. Um, yeah, that's basically a pretty like short introduction about the balloons, what it does. And now I will just hand over to Antti to take the rest. Yep.
Okay, thank you. Okay, I need to keep it very close. Okay, so what I wish everyone to remember from this slide is actually that a balloon is an object that associates a set of CPUs with a set of containers. And that set of containers will be executed on that set of CPUs and nowhere else. Okay, then first, let's see about the new OCI runtime enhancements that are, as Feruz told, already supported in runc, but there is not real Kubernetes high-level support for them yet. So first is a policy.scheduler, which basically configures and makes runc call this set attr, which configures Linux scheduler to policy and priority, which affects again that how this process, which has, for instance, real-time scheduler set FIFO policy set, so how that process is going to be handled by the Linux scheduler. And these real-time scheduling policies, where there are a couple of them in Linux kernel, they implement so-called a pattern that I would describe like as a winner takes it all. So when there is a process that is ready to run and it has a scheduling policy, the shed FIFO, it means that kernel will run it immediately. It will find a CPU. If there is someone already running there, it will kick it out so that this real-time policy and real-time process will get running there. And now we have NRI balloon support for this, as you will see later. Second thing that I want to mention is policy.io priority, which is a similar thing for IO scheduler. So when processes want to access IO devices, they create IO requests, and this Linux IO scheduler is responsible for selecting which IO request will be handled. And again, there is a class now with this real-time IO priority. And again, there is this winner takes it all pattern. So if there is one real-time class IO request in the queue, then that will be handled first and everyone else needs to wait in that case. Again, we have support for this in balloons. There are also other runtime spec enhancements like memory policy, but I'm not going too deep to that in this presentation because this is about low latency and that is more about optimizing memory bandwidth for AI and such workloads. So how does it look like in this figure where we have balloons policy NRI plugin? There is a CRD where we give this balloons configuration, and in this CRD we can define that here are the scheduling classes that we want to use for separate set of containers. As I mentioned, a balloon is associates a set of containers with a set of CPUs. So if we define, there's a real-time scheduling class, and it means that we want to set also not only the process scheduling policy, this is FIFO, but also IO class to the real-time. Then what happens when this kind of container is created? Balloons policy adds this information to the OCI spec that goes down to the runc, the low-level runtime, which then calls these syscalls to set the scheduling policy and IO policy correctly. And that way we have now tuned container running in a balloon. Another thing is about that was about configuring the containers and the processes in the container. But now I wish to also show about configuring the CPUs. And that the first thing is CPU frequencies that can be configured again with the CRD. So we can define CPU classes. For instance, here is a low latency class where we define minimum and maximum CPU frequencies for that class. But there is no CPU support in OCI spec, but that doesn't matter because these NRI plugins are running on the same node as a daemon set. They are typically deployed that way. So they can write directly to the sysfs and set the CPU frequencies as specified in this CRD. And because this NRI Palus plugin decides also exactly which CPUs this process is going to run on, and these containers are going to run on. So it knows that which CPU frequency should be adjusted as specified. Here I should also mention these power saving states. There is a CPU idle entry in sysfs where you can enable and disable power saving for each CPU. And as Feruz mentioned, it affects that there are several levels actually of these power saving states. There are very light level ones where the CPU is basically keeps on power and doesn't have its cache flushed or anything. So it will be very quick to continue from such a state. But then in the deeper sleep states, the CPU can be powered off and its cache can be flushed. So waking up from that kind of state takes much longer. So these are the controls now. Process scheduling priority and CPU frequency and CPU C states that I'm now trying to find an optimal combination and also trying to visualize to you the effect, what they actually have to the latency of a process. So here are the data points. The example application that I've been measuring here is such a thing that it sleeps 1 millisecond. So it needs to wake up roughly 1,000 times in a second. And what I'm measuring is the tail latency and visualizing actually the tail latency here. And it's normalized so that up there is 100% and y-axis 0 ends to the 0. And this is highly depends on the hardware and the processor type where you are running it. So for instance, CPUs in laptops may enter very deep sleep state in order to save battery. But on server side, it does have a great effect as well, as you will see. So first, let's draw some circles that only visualize the effect of CPU frequency. So just out of curiosity, I have forced first the minimal CPU frequency possible. So it's 800 megahertz is the smallest circle. Mid-sized circle is the default where CPU frequencies are not limited in any way. So it has a full range. In this particular CPU where I was running, it was from 800 megahertz to 3.8 gigahertz. And finally, the biggest circle is where we have locked the CPU frequency to 3.8 gigahertz. And this process that we are measuring is now in these figures. It's the only process that is running in the whole server. So figures are a bit different when there's a background noise, but we'll come to that later. Okay, then let's repeat these measurements in different C state, that is the power saving state configurations. So here we had all the power saving states enabled. What if we allow entering only the very lightest power saving states? Or what if we disable all power saving states? You can see that frequency matters. There's some differences, especially here in the lightest C state cases, that if we alter the frequency. But if we disable all power saving states, then the frequency doesn't actually matter that much. And again, let's repeat all these measurements in the case where we set the process scheduling policy. So this was with the default scheduling policy, and here we are using the real-time scheduling policy, Sched FIFO. And again, you can see that all these things matter. So no C states, lightest C states, and there at the bottom there is all C states disabled. It goes so close to the zero, so let's zoom in to the best 10% of this figure, so we can see the differences. So it really, here we can see that the best results can be get by disabling all the power saving states and using the real-time scheduling policy for the container. And in that particular case, what we still get from the maximum frequency is that there was some jitter, at least in these results, that disappeared. So in the end, what we got is 2% left from the default latency that we started with. Then some thoughts and words about the CPU frequencies. So there are so-called turbo frequencies where some CPU cores of the whole large Xeon CPU are boosting to very high frequencies, but you can't run all the CPU cores with that high frequency. So if there is only a single one, then you can boost up to the maximum frequency. But for instance, if there are like 16 CPUs out of 200 that would need very high frequencies, then you might not request, you might not get anymore the full frequency. And that calls for some way to allocate, some way to point out that if there are like only normal workloads, then any CPU core can boost to very high frequency. But if there is some critical workload where we want to ensure that this one actually gets the full frequency that we have and the others don't matter that much, then we need some solution for that. And this is now what is being developed in NRI plugins project in Balloons policy as a pull request. Is like this kind of animal that we have CPU classes that can be defined by a user, and there some free you can use like symbolic names for minimum and maximum frequencies. For instance, here take turbo CPU class says that both min and max frequency is the turbo frequency. And there is an additional field saying that this is turbo priority 1, which means that if there is a balloon with a higher turbo priority than the other balloons, then again, with a winner takes it all pattern, it will get the turbo and other ones won't. And if there's no such containers, no such balloons that would need this CPU class, then we can run with the default CPU class where we can use turbo given that it is available. Okay, here's an example output and link to my GitHub repo where you can find the whole thing, trying this whole thing out of scratch. So there's a Helm install commands where you can install Balloons policy actually from this PR where we have CPU classes enabled. And once there is such a real-time container running, this is how you can verify that which CPUs are exclusively given to that real-time container, which CPUs have C states and which C states disabled, and how are the min and max and current frequencies when read from the sysfs. Okay, so the summary of the whole presentation is maybe twofold. So first, this NRI it's really like a tweaker's holy grail. So if there are new OCI features, you can use them there, even though there wouldn't be such support for such things in Kubernetes. On the other hand, you can also directly control hardware knobs and whatever kernel is offering you. And regarding the low latency stuff, we just showed that you really need to handle both kernel knobs and hardware knobs. So you get both processes optimized and also the CPUs optimized where you are running those processes. Okay, that's pretty much it. Any questions?